In this video, we're going to go over notes 11 and 12 where we talk about addition reactions. Addition reactions are kind of a big deal in organic chemistry because there's many types, and we're only going to go over the most common. Okay, so what happens to an addition reaction is some sort of group, and I'm writing functional group, but it doesn't always have to be a specific functional group. Just some sort of group is added across a double bond. Okay, and it's essentially the opposite of an elimination reaction. In an elimination reaction, something comes in, takes the H electrons fall back, create a double bond, and cause the leaving group to leave. In an addition reaction, the double bond comes in, takes the H, leaving group leaves, and then later the leaving group comes back in and attacks an electrophile. And I don't expect that to make a lot of sense right now, but it will later. As a reminder, double bonds, even triple bonds too, but double bonds are nucleophiles. And so we're going to see that. If a double bond could be a base and specifically attack a hydrogen, sure, or it could specifically attack an electrophile. H plus is an electrophile, but when a nucleophile specifically attacks an H plus, it's called a base. Okay, so we have two positions. They're called vinylic positions across our double bond, the two carbons. And so the question is, H goes on one of them, so an H maybe goes there, and maybe X goes there. Or X could go here, and H goes here. And so the question is, where does X go? And it depends on the reaction. So we have something called Markovnikov addition. And in Markovnikov addition, what we have is our added group is added to the most substituted carbon. So what would that look like? Let's say we had something like this. We had a double bond and we added HBr. What that means is H is going to be added on one carbon and Br will be added on another, while your double bond will go away. Okay? If this is Markovnikov addition, this red carbon would be more substituted. And so what will happen if it is Markovnikov addition, bromine gets added there, hydrogen gets added there. Now, I don't know why I don't have it on here, but I'm going to add a note. My bad for forgetting. What's the opposite of Markovnikov addition? We have anti-Markovnikov addition. And this is basically where our added group is added to the least substituted carbon. And this usually occurs under the presence of peroxides, like hydrogen peroxide. And that's typically abbreviated ROOR for peroxides. Okay, syn versus anti-addition. Okay, syn means same, so we get the same stereochemistry. Okay, so what does that mean? That means if we have something like this, and I'm just going to make up a case. Let's say we had something like H2 added across that double bond, we would get wedge H and wedge H, or dash, or dash. Okay, they would be the same. Whatever we added would be the same. Anti-addition means we're going to get different or opposite stereochemistry. And this might be something like, let's say we added, and I understand that what I'm writing above the reaction arrow, we haven't gone over yet. We might get something like a wedge bromine and then a dash bromine, okay, where they're opposite. Okay, so I'm going to go over a lot of these. How these mechanisms work is we have a double bond that's needed for an addition reaction. And then whatever is over the arrow, that's what you should be really making some sense of into how it is reacting. Okay, so here's what happens is we are going to add a halogen, and that's typically bromine, chlorine, iodide, to the most substituted carbon. Here's what this mechanism looks like. This nucleophile attacks a hydrogen, and then the electrons go back to bromine. We're going to put the hydrogen down here. That's our added hydrogen, because that puts our positive charge on the most substituted carbon, leaving us with a tertiary carbocation intermediate. Bromide is still hanging around because they're in the same reaction vessel. So bromine cedes that positive charge and immediately undergoes a nucleophilic attack. And so we get bromine added to the most substituted carbon, while hydrogen is on the least substituted carbon. Now, that's Markovnikov addition of HBr. It could be HCl or HI, okay? What if it's anti-Markovnikov? I'm telling you, we don't need to worry about the mechanism here. But what we see is we see HBr, and this means dissolved in peroxides if it's underneath the arrow. So what this is going to do is this is going to add a Br group to the least substituted carbon. Okay, we're not going to worry about the mechanism here. We don't have the background info to understand free radical chemistry just yet. Okay. Now, here we have acid-catalyzed hydration of water. Okay, so this is going to add water to the most substituted. But rearrangement is possible. Okay, so methyl shifts and hydride shifts still come into play here. When you dissolve sulfuric acid in water, if you look at the pKa's, the pKa of the sulfuric acid product after it reacts with water is much higher than, the pKa of hydronium, the product here, is much higher than the pKa of H2SO4. And so these guys, if we take sulfuric acid dissolved in water, I like to cross them out and just show that we form hydronium. That's truly the species here that's going to be reacting, even though it's commonly written like this. Okay, so we're not adding any sort of sulfur group. We're going to add water, which is almost always going to be an OH group. Okay, so watch how this works. This will feel kind of similar to an SN1 reaction. we're going to come in, we're going to take an H, electrons go back. We are always going to put our H where the positive then goes on the most substituted carbon. That is a tertiary carbon, so that's stable, tertiary intermediate. And then water is a nucleophile. It's not the world's strongest nucleophile, but it's still a nucleophile. Comes in, attacks the positive, brings with it its two H's. We know oxygen with the 3 bonds will have a positive charge, but we're not going to leave it like that. Water will come back in, take off an H, give the electrons back. And we're going to get OH, okay? That is what that product will look like. Notice that we've called this acid catalyzed because we started with water and, not water. We started with hydronium, and then at the end, water comes back in, reacts with an H plus to form hydronium again. So it is truly a catalyst reaction. Catalysts are neither consumed, they're not consumed in your overall reaction, but they do end up reacting. So maybe halfway through, your catalyst might not be there, but it'll be produced at the end. The reason why this is annoying is that we could have some issues with rearrangement, and we'll talk about that later. So we can do this same reaction where we add water to the most substituted carbon down here. This is called oxymercuration, demercuration. So we add water to the most substituted carbon, no rearrangement will happen. Okay, and that's ideal. I can't write today, goodness. Okay, notice we have 1 step and then 2 steps. So even though this sodium boryl hydride is underneath the arrow, because it has a 2, that doesn't mean we're dissolving mercury acetate in there. What it means is that the first thing is to take this compound, react it with this, then whatever it forms, we'll react it with sodium boryl hydride. Okay, so we're not going to worry about the mechanism here. In college, you'll definitely have to worry about the mechanism, but what we've got to decide is which carbon, left or right, is our most substituted. It is our left, so an OH group gets added there. Now, we're going to do the same thing, except what is going to be different here? We're going to add water or an OH group to the least substituted. A good trick to know that you have the least substituted is I see peroxides there. So my product is going to look the exact same, except I've got to decide top carbon or bottom carbon, which one's least substituted. Whatever one's least substituted will get the OH group, and that one is the bottom carbon. Okay, catalytic hydrogenation. This platinum is a catalyst. Again, we're not going to worry about the mechanism. I forgot to write that here. Don't worry about the mechanism or the steps involved to get the final product. Same thing here. Don't worry. Okay, this is a catalyst. Typically, it's a transition metal like platinum. And so what happens is we're going to add hydrogen across a double bond. So what we get is the same thing, except now we have hydrogen and hydrogen, which we wouldn't normally write, but I'm only writing just to show that the double bond is essentially removes double bonds. Okay, we've got a few more here, just two more, and then we're going to do some practice. And we do need to worry about the mechanism here. This mechanism makes sense. So what we have is we have Br2, which I'm going to draw Br. Okay, and I'm not going to worry about lone pairs on the bromine. And that's a non-polar molecule. It absolutely is. But electrons are moving around, and so in a perfect world, they would both have the same electron density. But from time to time, one of the bromines gets a little bit more electron density than another, and that's what is called a temporary dipole. And so one of the bromines, just for a fraction of a second, will become like an electrophile because it has less electron density than normal. So what happens is the double bond attacks one of the bromines, the electrons go back to the other bromine, and for convenience, let's add a methyl group here. So what we've got to understand is what makes sense where to put the bromine. We could put the bromine on this carbon or on this carbon, but understanding that whatever carbon doesn't get the bromine, the other one is going to get a positive charge. And so the answer should be that we want to put the bromine on the bottom carbon because that'll put a positive charge on a tertiary carbon, and that is more stable. That Br minus, that was the leaving group, then is still around, and it comes back in a nucleophilic attack and is going to add on to where that positive is. So this essentially adds bromine across a double bond. Okay, last one. Halogenation with water or alcohol present. Okay, so this one's going to start out very similar. We have bromine dissolved in water. So we have Br, Br. And my nucleophile attacks, takes the Br. We're going to put the Br on the bottom carbon like we talked about before because that puts a tertiary intermediate which is going to be more stable. Now, if this were just Br with no water, a second bromine would come in and attack the positive, but that's not what we have here. The second bromine is actually very content to stay by itself. What we have is we have water. Oxygen is actually going to be a stronger nucleophile than a negative bromine. So what happens is the oxygen in water adds and we get water added. We know water or oxygen with 3 bonds will be positively charged. And so our last step is always for water to come back in, take off an H. And that way we've added an OH group. So this adds a bromine, it could be chlorine or iodine as well, to the least substituted. And an OH or OR group added to most substituted. Okay, so how could this be all different if instead of water it was an alcohol? So what I'm going to do is I'm going to delete all of this. And we're going to try it. Oops. Down here. What if instead of water, let's say it was ethanol? It's still going to start out the same. Take a bromine. Bromine gets added to the least substituted, so we have a tertiary intermediate. Oxygen, a neutral oxygen is a stronger nucleophile than a negative bromine. Oops. The oxygen comes in, nucleophilic attack on the positive charge. We get OH positive plus the ethyl group. Ethanol then comes back in, takes an H, gives the electrons back. And here we didn't create an alcohol group, but rather we created an ethyl group, or ether group. Okay, so let's predict the products for the following reactions. On this one, we need to draw the mechanism. We have take the H, put the positive on the most substituted. What I need to do, I don't think I wrote it, but I'm going to go back and write it, is that rearrangement is possible for HBr, or HCl, or HI. And we see one here. This is secondary. If we did a hydride shift, that will make this a positive there, that hydrogen's there that we just shifted, and then negative bromine can come in. Okay, what if we have HBr in peroxides? This, we're not going to worry about the mechanism, we just add bromine to the least substituted, so we get a product that looks like that. Okay, go ahead and practice these on your own. You can draw the mechanism for the first one at least. I'm not going to worry about stereochemistry in these notes. Okay, let's look at this one. I'm just going to do a lot of examples because it just takes a lot of experience to get these down. Here we see HCl instead of HBr. Put the positive on the most substituted. Here, we're going to have a methyl shift. And then Cl minus can come back in. Now, you probably are thinking to yourself that methyl shifts and hydride shifts are very tedious, and they are. That's why we're going to look at these two reactions. H2SO4 H dissolved in water is really H3O plus. Our double bond nucleophile comes in and attacks an H, gives the electrons back. We're going to put the H on the most substituted, or the least substituted carbon of the group. That way we put it here. And let me just see. That is tertiary, but let's say we could hydride shift or methyl shift if needed to. That can happen here. And so that's why it's not ideal to use H3O+, but sometimes you don't have any options. Water comes in, adds to the positive. Oxygen with 3 bonds will be positively charged. We're not going to leave it that way. Water comes back in an acid-base reaction and takes off one of the hydrogens, and we've added an alcohol group. The thing that's nice with mercury acetate dissolved in water and then sodium borohydride is that this adds an alcohol group to the most substituted, so we get something like this. If we had this with H3O+, here's how this reaction goes then. we get a hydride shift. And that essentially puts it on from secondary to tertiary. Then water comes in. Water comes in again. We have plenty of water around, and we finally get our alcohol group. But notice with H3O plus, it's not on either of the carbons that were in that double bond. That's why this, in my opinion, if you don't want to think about hydride shifts or methyl shifts, this is a far superior method because it doesn't have any rearrangements. Okay. If we have BH3 dissolved in THF and then peroxides, we need to know that that adds an alcohol group to our least substituted. Same thing here. Our least substituted is going to be this bottom one, and those are very nice and straightforward. If we have Br2, it's going to add Br to across a double bond. But if we have Br2 in water, and I'm not drawing the mechanism here, we're going to have bromine added to the least substituted and then an alcohol group added to the most substituted. Okay.